resisted motion horizontally. Okay, so with this, a particle moves with mass m. So the mass equals m. And kilograms, and it's moving horizontally to the right. So there's my little diagram down there. The resisted force is minus mkv because it acts against it. That's why it's negative. It starts at O and it's moving in this direction. Okay. So first of all, just to set up our equations of motion, the sum of the forces is mass times the acceleration. And the total forces here is minus mkv. So the m actually cancels out and the acceleration is equal to minus kv. So the first one here, we want to get v in terms of x. So we replace it with v dv on dx. Okay, so go v dv on dx is minus kv. The v's cancel. So that means you got 1 dv equals minus k dx. You integrate that, you get v equals minus kx plus c. So x equals 0, v equals u. So that means u equals minus k times 0 plus c. So therefore c will equal mu, the initial velocity. So what that means now, so c it would equal mu, and then what that tells us is v equals minus kx plus c, so it'll just be plus mu. So it's mu minus kx. Okay, part B, if you want to get v in terms of t, so acceleration equals minus mkv. You need to put it as dv on dt to get it in terms of t. And then when you split this, you get 1 over v dv equals minus mk dt. So when you integrate both sides here, you get ln of v equals minus mk t plus c. So initially, when time equals 0, v is equal to mu. So you go ln mu equals minus mk times 0 plus c. So c is equal to ln of mu. And then from that, we can put it back into our formula. So ln v equals minus mkt and then plus c, so it's plus ln mu. If we put the lns to one side, so you got ln v minus ln mu equals minus mkt. That way we can group the logs together. Equals minus mkt. So v over mu equals e to the minus mkt, because basically that is a log base e. So if you use like the raising the power, so it's like the 7th rule, e to the power equals the number, and v equals mu e to the minus mkt. Now, it said that initially it was moving to the right, so you just take the positive version of this. Because it's an absolute value, it could be plus or minus, but you take the positive version because it's moving to the right initially, and it needs to satisfy the initial condition. So just to make sure that we got all that. So basically, if you make both velocities, this velocity and that velocity, equal, you can rearrange it to get x and make x a subject, and that's how you get this displacement here. And then to get the limiting displacement, you make the time go to infinity, and if you make the time go to infinity, the 1 over e to the mkt, the bottom gets bigger and bigger, so 1 over that will go towards 0. So then you just end up with mu on k times 1. So that means the limiting displacement would just be mu on k. And that's the limit of your displacement. Okay, so a particle of mass m kilograms is projected right horizontally with a velocity of mu meters per second, and the resistance force is mkv squared. So here's your object, you're moving that ray, that's positive, that's negative. The resistant force is mkv squared. Okay, so part A. Find the acceleration in terms of v. So mass times acceleration will equal the sum of all the forces. The resistance force is actually negative, so it's negative mkv squared. So the acceleration is minus k, because the m's will cancel out, v squared. Okay, part B, find v in terms of x and v in terms of t. So part 1, let's go, v in terms of x, so acceleration is minus kv squared. We also know time is 0, x is 0, and v is mu. Okay, so that means you replace the acceleration with dv on dx, so it's minus kv squared. Cancel the v out, divide by the v, equals minus k dx. So that's moving to there. So now we're going to integrate it. So we get ln v equals minus kx plus c. So x equals 0, v equals mu. So ln mu equals minus k times 0 plus c. So that part will just go, and c is just equal to ln mu. So if we put that back in now, we have ln v equals minus kx plus ln mu. And the aim now is just to get v as the subject. So to make v as the subject, we actually need to move the logs together. So it's ln v minus ln mu equals minus kx. So that's ln v in absolute value on mu equals minus kx. So it's log base e, v on mu equals minus kx. So that means v on mu equals e to the minus kx. It doesn't matter if the mu is in absolute value or not, because it's positive anyway. v equals mu e to the minus kx. Now this is initially moving to the right, so therefore you just take the positive mu e to the minus kx. And that's v in terms of x. Okay, so now we need to get v in terms of time. Okay, so let's go part 2b. So we start with the acceleration is minus kv squared. We replace acceleration with dv on dt, so it's minus kv squared. Bring the v over there, so you get 1 on v squared dv equals minus k dt. Integrate both sides. So when you integrate that, you want to bring that up to the top, because then you can integrate it, because it's not a power of 1, therefore it's not a log. And then that side will just be kt plus c. So it's v to the minus 1 and minus 1 is kt plus c. So that's minus 1 on v equals kt plus c. So to find the c, v equals mu, t equals 0. Therefore, minus 1 on mu equals k times 0 plus c. So out of that, we get c equals minus 1 on mu. So then let's put it back into the equation. So you get minus 1 on v equals kt minus 1 on mu. Get a common denominator. Minus 1 on v equals k mu t minus 1 on mu. Let's change the sign. 1 on v equals 1 minus k mu t on mu. And we want to get v, so flip it. Flip both sides, because if a on b equals c on d, then b on a equals d on c. It's still the same fraction. So V will equal mu over 1 minus K mu T. And there you go. So what we actually have there is V in terms of T, and up here we had V in terms of X. Now the next part is to find X in terms of T. Now you can do that in a couple of different ways. We could make these two things equal and rearrange. But if you want to get X in terms of T, another way would just be to use this one. I'm just going to use this one this time. I've made the two things equal before. So I just want to go through. You change the V to dx on dt equals mu e to the minus kx. Dx on dt equals mu on e kx. Swap them over. So e to the kx equals dx. Mu dt. Integrate, integrate. 1 on k e to the kx equals mu t plus c. Okay, so time equals 0, x equals 0. So 1 on k e to the 0 equals mu times 0 plus c. 1 on k times 1 equals mu times 0, which is 0 plus c. c is 1 on k. 1 on k e to the kx equals mu t plus c. And c we found was, what did I find for c? We found c was 1 on k. Okay, so if I multiply everything by k, I get e to the kx equals k mu t plus 1. And then if you ln both sides, you get e to the kx equals ln of k mu t plus 1. This will come down, so you get kx equals ln k mu t plus 1. And then x is 1 on k ln k mu t plus 1. And that is the displacement in terms of time. Now, I think the question really here is, does this one actually have a limiting displacement? Like if you made time go on to infinity, would it have a limit? Now as time goes on to infinity, KUT plus 1 will go on to infinity. Now when you log it, if you think about the log graph looks like that. So it does actually go on to infinity, it just goes on at a less rapid rate than it normally would if it was just a number. So it has no limiting distance. It will just keep going on and on and on. So it has no limiting displacement.